Hi, and welcome back to week 7. This week we're doing systematic reviews of research evidence, and we're going to discuss meta-analysis, meta-synthesis, and a mixed studies review. So this week, you definitely should be working on and completing your meta-analysis table. We will work on that in class in groups. That way, if you have any questions or you want to run some things by your colleagues, we can definitely do that. I'm also going to review the meta-analysis table as well as our rubric that we've been basically working on since we started the class. So here we go. So here is a follow-up again about the rubric. I just wanted to share this screen again. This we talked about back in week 4. At this point, we've really completed chapter 1 in terms of gathering all of this information. We've worked on an introduction of the research problem that you guys have created, background of your problem, significance of the problem, your purpose statement, your PICO question, conceptual and operational definition in which you've developed a framework, and how you're going to conduct your research. At this point now, we're working on your hierarchy of literature, your literature review through your meta-analysis grid, your inclusion and exclusion criteria through your search terms that you have been hopefully recording or keeping track of so that you can put it in a written format within your rubric. Search strategies and yields. We worked on that in a discussion board to practice, how you search for your research literature review. So this is where we're at this point. And remember, you're gathering all of this data through your class, your current class, which you will put together in your class 2. This rubric will end up probably being about 40 to 70 pages in length, but that includes, a tremendous amount of information that you're gathering, including your meta-analysis grid, which will probably be 5 to 10 pages, your references, your appendices, all of that is included within this rubric. Next, I just wanted to review the hierarchy of evidence again. Within your meta-analysis grid, we are going to add that you should be including what level each article is in level 1, level 2, level 3 within the first column of the grid. So here we have the grid. Right now you have the citation, the author, date of publication, and title. You're also going to include your level of evidence within this area of the grid. Okay, so just so you know, keep in mind, you want to try to have, a well-rounded grid that includes, at least a few of level 1, level 2, level 3. I know some of you have mentioned that you're only getting the lower levels, but remember, this is your highest level of evidence in this top 3 of the grid. So you really want to try to have a strong foundation of evidence for your research. And remember, when you're doing your search for your literatures, your articles, you will find that you can go outside of your discipline or look at different search terms if you need to validate whatever it is you're researching. That includes if you're doing a qualitative study, you could look up quantitative type studies or vice versa. All right, just so you know. This, is an example of the meta-analysis grid. You do have a template for the grid on the discussion under your modules, under this current module week number 7. So Professor Alana did post another template if you needed it. A few things to remember in terms of filling out your meta-analysis. First of all, remember within the grid, we do expect that you are going to have between 10 to 12 strong articles, okay? You'll probably end up reviewing between 30 to 40 articles in order to find what you need, including the different levels of evidence. So you just prepare yourself to find 30 to 40 articles and really look through them to make sure they are adequate amount of data for your research, okay? Remember, this is a tool to help you develop your own research. Focus on extracting information from the articles that pertain to what will help you develop your particular project. We don't want you copying and pasting within your grid. We want you summarizing and really pulling out key points that are going to help you remember what information you pulled out of these articles. When you look back at this grid in another few weeks, you're not going to want to reread articles to find information that might help you write your rubric. You want that within your grid so that it's already there and you can just pull it and remember what you had found. All right. A lot of the times you're going to read the articles, and some of the information you may not even understand, because it does get very complex. Don't focus on that information. Focus on the information you understand that really solidifies what it is you're trying to prove within your research. We also want you to include within the grid, why did you include this article? What did you help, what do you feel helped strengthen and provided a foundation to your research, that you pulled out of the information that you got from the article? You could include that in the column on appraisal of worth to practice. Okay, that's your last column within the grid. Okay, for review, true or false? Tell whether the following statement is true or false. Evidence-based practice relies on rigorous integration of research evidence on a topic through systematic reviews. Is this true or false? Evidence-based practice, EBP, relies on rigorous integration of research evidence on a topic through systematic reviews. Now remember, where does systematic reviews fall on your grid? Okay, remember that's one of your strongest evidence, that's level 1. So is that true or false? EBP relies on rigorous integration of research evidence on a topic through systematic reviews. The answer is true. Evidence-based practice does rely on rigorous integration of research evidence on a topic through systematic reviews. A systematic review methodically integrates research evidence about a specific research question using carefully developed sampling and data collection procedures that are spelled out in advance in a protocol. Okay, another question for review. Tell whether the following statement is true or false. Systematic reviews of qualitative studies often involve statistical integration of findings through meta-analysis. Reviews of qualitative studies often involve statistical integration of findings through meta-analysis. Is this true or false? This is false. Why? Systematic reviews of quantitative studies often involve statistical integration of findings through meta-analysis. Remember, quantitative involves numbers, which is statistical, right? A procedure whose advantages include objectivity, enhanced power, and procedure. Meta-analysis is not appropriate, however, for broad questions or when there is a substantial inconsistency of findings. Okay. So the one thing I just wanted to point out in terms of meta-analysis, we are calling your grid a meta-analysis grid, but keep in mind this term meta-analysis is an umbrella term. Do not get confused, because there's a difference between what we're talking about in today's PowerPoint, where between a systematic review and a meta-analysis review. The meta-analysis, can be used for, like we're doing, this grid in terms of putting together lots of research articles that you yourself, the researcher, are reviewing. So we are calling it, the term we're using for the grid is meta-analysis, but it is an umbrella term. So in this particular video, you're going to get a little more clarification of what a meta-analysis actually is in terms of the levels of hierarchy of evidence. So we'll just watch this. It's a good little synopsis.
This is an introduction to the concept of systematic literature reviews and meta-analyses. What do you think of when you are asked to conduct a literature review? Your answer will probably vary depending on your past experiences with literature reviews, through class projects, as a precursor to future research, or as an effort in and of itself. Literature reviews may take many forms and use different methodologies depending on the purpose of your review and/or the question you aim to address. Approaches may be selective, where authors are just looking for some resources to illustrate a point, while other methodologies require an exhaustive search and comprehensive set of information. Reviews also vary with regard to the extent to which authors assess the quality and/or risk of bias of each included reference. There are other considerations too, but these two continuums will be helpful to conceptualize the landscape of literature reviews. The approach we are likely to think of when we first hear the term literature review probably falls into the category of traditional reviews. These tend to be descriptive overviews or topic summaries, sometimes presented as a means to provide background to a larger work, and sometimes as a standalone review, providing trends, updates, common practice, or a broader overview of a topic. Reviews that fall into this category also vary with regard to structure. In some cases, the approach an author takes to find, select, and review material is not explained at all, whereas other approaches might fall into a loosely defined category of structured reviews. Systematic reviews, on the other hand, are highly structured, clearly defined, and aim to be comprehensive and account for bias and/or quality of a material that is included in the review, as well as the bias and/or quality of the review itself. It's easy to confuse the concept of a structured review with a systematic review, as the terms are so similar. However, the term systematic review refers to a very specific procedure that requires authors to adhere to published protocols and reporting guidelines. The systematic review approach aims to answer a specific question or set of questions by collecting, evaluating, and synthesizing all available relevant information. The result is a qualitative discussion of existing information about a topic, how the references do or do not speak to one another, gaps in the field, trends across research, and how available evidence may inform actions or decisions. Systematic reviews may also include a quantitative synthesis, often using the statistical approach called a meta-analysis. In short, meta-analyses take the findings from several studies to create a new statistic. This new analysis is based on the combined samples of included studies and is therefore more powerful than the results of the individual studies it comprises. Finally, a cornerstone of the systematic review is transparency and replicability. In other words, the review should be documented and reported with enough detail that another research team can accurately replicate the approach. Because of these characteristics, the systematic review and/or meta-analysis is considered the pinnacle of quality when it comes to evidence for decision-making. Thus, despite the fact that systematic reviews are reviews of primary research and/or other information, they provide a unique and significant contribution to the field. Therefore, a systematic review is considered original research in and of itself, and is typically pursued and published as a standalone project. As you may have guessed, the systematic review is resource intensive, requiring a large time commitment and a full team of individuals with specific expertise related to each stage of the review. Generally speaking, you should plan to spend at least 1 year working with at least 2 other individuals if you choose to pursue your own systematic review. We'll discuss these requirements in more detail throughout this series. Pursuing a systematic review is a great opportunity for your team to strengthen their understanding of a research area and to assess methods in your field. Likewise, these publications tend to be highly cited and provide a strong research record that can help when you're applying for grants. You might find that a systematic review approach doesn't fit your research question or current resource conditions, but there are other kinds of comprehensive reviews that you may consider. For example, we use scoping reviews to map or illustrate the field of information related to a comparatively broader question. And restricted reviews, or rapid reviews, is a term for systematic review with some kind of constraint, such as a tight deadline, a restricted search, or not having access to a full team. So, looking at the literature review landscape, you can see how different types of reviews might fall upon the matrix. Likewise, you've probably noticed that the range within each type is broad, as there is a lot of variation between and within each category. Choosing the right approach for your question, objectives, and capacity is important. In this series, we'll be focusing only on the systematic review and meta-analysis. However, the tools and approaches we cover are valuable for any review type. If you are interested in exploring any of the other review types that exist, please check out the additional reading for this video and/or ask a librarian for help. You can also check out the resources accompanying this video to learn more about the support and services from the Evidence Synthesis Services team at the University Libraries at Virginia Tech.
So that's super helpful in terms of just getting a broad understanding of systematic reviews and meta-analysis. I also want you to keep in mind, a lot of you have asked about your grid and including a systematic review. Do you need to take, each article within the systematic review and break it down in your grid? No, you do not. What you should do is just include the articles and the consistent common themes within your grid from the systematic review that apply to your particular research. The other thing I also want to point out in terms of your grid, when you're listing your different articles, try to keep your articles that have consistent or similar themes together. So like articles 1, 2, and 3 that you include in your grid, those should have the same sort of subject matter or theme. You want to try to keep them organized within the grid together, just to keep it more consistent and more user-friendly in terms of using this as a tool to refer back to. So again, in terms of systematic reviews, you should only really include the information that applies to your particular research, and try to summarize what it is you're finding that is helpful for you. You don't need to break down each article. And then when you do list articles within your review in the grid, try to keep them theme-based organized. So 1, 2, and 3 are about diabetes, and 3, 4, and 5 are about obesity related to diabetes, that kind of thing. Okay, synthesis versus analysis. Here's a very good video on differentiating those two.
Hello, class. Today we will be discussing the topics of synthesis versus analysis. Most of us may ask, what is a synthesis or an analysis? And today we will get into much more detail about each of these. The most important piece of information to understand is the fact that a synthesis and analysis are opposites. What exactly is a synthesis? A synthesis is combining multiple sources or ideas into a whole in order to understand shared qualities between each individual. To better understand what a synthesis is, let's take a look at a few examples. We're going to look at 2 different examples. The first example would be taking an individual pieces of a puzzle and putting them together to make a finished puzzle. And the second example would be combining different chemicals to form a more complex compound. So then, what is an analysis? An analysis is breaking down the text or the problem that you are examining in order to understand each individual part and to see how it works. To better understand analysis, we will look at the same 2 examples as before. The first example would be taking apart an already completed puzzle to look at all the smaller pieces that make up the puzzle. The second example would be breaking down a chemical compound to look at the individual components that make up the compound. So, there are 2 types of synthesis that we will look at today. The first is an explanatory synthesis, and the second is an argument synthesis. Now let's take a look at each of them in further depth. Let's start with an explanatory synthesis. An explanatory synthesis helps to understand the topic. It divides the subjects into its components, and it only tells you what's obvious as the reader. Next, we have an argument synthesis. This one is right to the point, and the main point of the argument is to present your own point of view to the readers. So how do we use synthesis and analysis in our writing? When writing a synthesis, we need to look at all of our sources and highlight similar key points. We also need to highlight the similar ideas between each of them. Next, we'll take a look at the analysis. When writing an analysis, we need to look and see how the sources support and disprove the argument. We need to see how each source differs from one another, and we need to use comparing and contrasting to get the best results. A few tips for writing your synthesis and analysis. Do not just summarize for your analysis. And a synthesis and analysis can be used on any type of writing. hope you were all able to identify the difference between synthesis and analysis after this short video. Have a great day.
So hopefully that clarifies synthesis versus analysis. Like I said, we're using meta-analysis for this particular grid. Nope. But I don't want you to get confused between the two. Okay, so here's a video. It's about half an hour. This is the final slide. You know, this is really a really good comprehensive intro to meta-analysis. So I found this would be really helpful for you guys to really grasp what a meta-analysis is. All right.
Well, hello there. My name is Thomas Kramer. I'm a PhD student at the University of Texas at Tyler, where I'm studying talent management for high potential employees. This module serves as an introduction to conducting meta-analyses, and it's based on a 2010 article by Field and Gillette, which you'll find cited in the reading list accompanying this video. This presentation will cover 4 elements of meta-analyses, namely the what and why, as well as a 6-step process as outlined by Field and Gillette. We'll wrap up with a demonstration of a simple meta-analysis in SPSS and R using the sample data provided in the article by Field and Gillette. So as we get started, we want to understand exactly what is a meta-analysis. The quote from Field and Gillette, I think, sums it up nicely. That is, meta-analysis is a statistical tool for estimating the mean and variance of underlying population effects from a collection of empirical studies addressing ostensibly the same research question. So meta means studying the thing itself. So a meta-analysis is the study of studies. Now, individual studies can be based on small sample sizes with potentially more biased estimates of effects. A meta-analysis works to homogenize results across several studies. Understanding the what of meta-analysis brings us to the question of why researchers elect to conduct a meta-analysis. And Field and Gillette introduced 5 key benefits of meta-analyses. There's a problem with estimating population level effect sizes from small sample level effect sizes. In other words, it's difficult to translate findings from a small group of people to an entire population, especially when the group of people is very small. So while not a result of a meta-analysis calculation, replication is considered and analyzed as part of the meta-analysis write-up. Now, because a meta-analysis considers similar research across a spectrum, it helps to address replication and reduce the effects of measurement error. And meta-analyses are particularly useful for other researchers because they assimilate and synthesize the previous studies and research into one handy article. So it's like an integrative literature review. A solid meta-analysis article on your chosen topic is worth its weight in gold. And if you can find one, you're super lucky. We start getting to the meat and potatoes of meta-analyses as we look at the mean and variance of underlying population effects. In the sample data sets, Field and Gillette look at studies of the CBT on anxious children relative to another treatment. And this can be addressed by meta-analysis, whereas a single study would be more applicable to the sample rather than the entire population. Now, variability in effects across studies is also considered the homogeneity of effect sizes. In other words, how similar are effect sizes across multiple studies? And Field and Gillette point out a couple of key points here. You would think that researchers want homogeneous effect sizes, that is, effect sizes across the studies to be roughly the same. However, growing evidence suggests effect sizes should be heterogeneous because significance tests of this variability have low power. So Field and Gillette propose reporting variability statistics regardless of whether the moderator variables have been measured, because they tell us something important about the distribution of effect sizes in the meta-analysis. Now, finally, moderator variables. Moderator variables help to explain the variability in effect sizes. Now, we just talked about the heterogeneity in effect size being desirable, but these moderator variables help explain that variance. And now that we've considered the what and why of meta-analyses, let's take a look at Field and Gillette's 6-step method for conducting a meta-analysis. First, we'll go over each of the steps, as you can see outlined here, and then I'll go through a demonstration of the method with both R and SPSS. Now, like any research endeavor, your first step is a literature search. You're looking for studies that have addressed generally the same research questions you're looking to analyze. And this is part of the beauty of meta-analysis. The studies do not need to be answering the exact same question or even use the same instrument. And that's why it's important to have a clear research question in mind when you conduct your literature review. You're looking for empirical research that attempts to answer the question you're posing. Now, it's perfectly okay if they frame it a little differently, use a different instrument, or even a sample with different demographics. There are really 2 things you're searching for when conducting a literature review for your meta-analysis, and that is articles and authors. The articles are obvious. You're searching for previous empirical studies that answer the questions you're looking at. But you also want to take note of the journals and especially the authors who are conducting this research and looking into these types of questions. You'll see why that's more important in just a minute. One of the potential limitations or biases of a meta-analysis is unpublished research. This is generally addressed in what's called the file drawer analysis, and we'll get to that in just a moment as well. Contacting researchers known to publish on the topic of interest is a great way of either finding additional articles or even unpublished research that may inform your file drawer analysis. It's a way of covering your bases and finding all of the relevant research that you can. The Field and Gillette article cites an example study by Cartwright, Hetton et al. This research team scoured 8 databases for articles. They then searched the reference list of the articles that they found. They also hand searched through 13 journals they knew to publish on their topic. Finally, they reached out personally to authors known to research the topic and inquired about unpublished research that those researchers may have had. Now, obviously, this is a very comprehensive strategy that ensured these authors covered all of their bases and found as many relevant articles as possible. Semi-simultaneous with your literature search is developing a very robust inclusion criteria. This is something you will keep in mind during the literature search and then apply rigorously with your collected articles. Concerns of bias in the selection criteria for meta-analysis should not be underestimated. The research you select will affect the outcome of your analysis, so bad data in will equal bad data out. One of the first concerns is the quality of the research you're including. Like the saying, one bad apple spoils the bunch, one bad study can sort of ruin your meta-analysis. Let's clarify exactly what I mean by a bad study. Certainly a bad study is one in which the research was conducted poorly, but a perfectly good study may be bad for your analysis because it doesn't answer a similar research question. It doesn't answer the question that you're looking for. So for these reasons, it's important to consider not only the inclusion criteria, but your exclusion criteria as well. There is a potential for exclusion bias when exclusion criteria are not considered. The Field and Gillette give an example in their paper for a meta-analysis of therapeutic interventions. That might require the researcher to select a definition and exclude studies that do not conform to that specific definition of therapeutic intervention. As Field and Gillette state, you can't come up with exclusion criteria on a whim, or you're going to start to introduce subjective bias into your analysis. In other words, set your criteria and then apply it and be very consistent in your approach. One of the best ways to protect yourself against concerns of inclusion-exclusion bias is to be perfectly transparent in disclosing your criteria and even justifying the criteria that you've set. One way of dealing with weaker studies that you'll still need to include is to group your studies by strength of their methodology. You could then see if such categorization moderates the effect size. As a final note, Field and Gillette cite a meta-analytic review by Cartwright, Hetton et al. That demonstrates a variety of inclusion criteria. The list that they have is very intentional and defensible, so really a good opportunity for you to take a look and sort of mirror what it is that Cartwright, Hetton et al. Has done. And that brings us to step 3, calculating effect sizes. So to recap, we've conducted a literature review and applied robust inclusion and exclusion criteria. We now have a stack of empirical research articles we can use for our meta-analysis. And our first step is to calculate the effect size from each study. Let me quote Field and Gillette here because they explain this very succinctly. An effect size is usually a standardized measure of the magnitude of observed effect. As such, the effect sizes across different studies that have measured different variables or have used different scales of measurement can be directly compared. So while many measures of effect size have been developed, the 3 most common that we're familiar with are Pearson's R, Cohen's D, and the odds ratio, all of which happen to be standardized effect sizes. And standardized effect sizes are typically used in meta-analyses in particular because they help you compare results across studies. Pearson's correlation coefficient, as it's formally known, or Pearson's R more commonly known, is perhaps the most commonly used effect size measurement. Now, it's well known and understood in our field, so that's a bonus for it as well. Essentially, Pearson's R measures the strength of the relationship between variables. Another benefit of Pearson's R is the numerical value is constrained between -1 and +1. So 0 would be no effect at all, and 1 is a perfect effect, either positive or negative, depending on where it is on the number line. I should point out that this is not a linear scale. In other words, an effect size of 0.4 is not twice as strong as an effect size of 0.2. And finally, if R is used, the effect size should be adjusted based on the reliability. So Field and Gillette state, that could be the base rate suggested in the literature, the average base rate across the studies you're analyzing, or a 50-50 base rate, which maximizes the correlation. Cohen's D is another commonly used effect size measurement and is based on the standardized difference between 2 means. Field and Gillette state that Cohen's D may be favored when the group sizes are very different. Some studies with large groups and some with relatively small. In these cases, Cohen's d would be better than Pearson's r. However, Pearson's r and Cohen's d can be translated back and forth regardless of the group sample sizes, so this is not that big of a concern. Next up, we have odds ratio, or OR, another standardized effect size measurement. The OR is the ratio of the odds, or the probability, of an event occurring in one group compared to another group. This measurement is less common than both Pearson's R and Cohen's d. That's probably why the inventor didn't attach his or her name to it. Once you've chosen an effect size measurement appropriate for your study and research questions, it's time to find or calculate the effect sizes. Now, you may look out and have studies that report effect sizes in your desired measurement, say Pearson's R or Cohen's d. Let's say that we've selected Pearson's R as our desired effect size measurement. We would then go to each study and look for R coefficients for each effect we're including in our meta-analysis. If effect sizes are reported but in a different measurement, say Cohen's d, there are many online calculators and spreadsheet downloads that we can use to convert back and forth between different measurements. If the study does not include an effect size, nor sufficient data for us to calculate the effect size ourselves, we'll need to contact the authors to see if they're willing to share the raw data, or at least the necessary statistics for us to compute the effect size. Now, we got to caution you here, be careful about simply tossing that study because it's too hard to find the effect size. This would certainly and obviously introduce bias into the results of our meta-analysis. Now we get to the fun part. We've laid the groundwork and are ready to start conducting our meta-analysis. First, we need to decide on our model, fixed or random. A fixed effect model makes the assumption that the studies sampled are from a population with a fixed effect size. So in other words, it could be predicated or predicted from just a few predictors. So knowing that, the effect sizes of the individual studies should be homogeneous because they come from the same population. For a random effect model, we assume the average effect size varies from study to study. They're heterogeneous. Field and Gillette argue that the model you choose, either fixed or random, is really only differentiated by the sources of error. So for fixed effect models, error is due to sampling studies from a population of studies. Error in random effects models is created by sampling the populations from a superpopulation, in addition to the sampling error or fixed effects models. So how do you choose between a fixed or random effects model? We need to consider two things: the assumptions that can be made about the populations in our target studies, and the nature of the findings we want to make with our meta-analysis. Now, articles by a host of researchers have found support for variable population parameters in the social science fields, so a random effects model is likely the best fit within our field. On the question of what type of inferences we want to make with our meta-analysis, a fixed effects model will only allow for inferences to the studies included in that meta-analysis, whereas a random effects model allows for generalizations beyond the included studies. Now, since we typically want to generalize beyond just the studies in our analysis, we have additional support for choosing a random effects model. Got one more thing. Remember earlier I said we wanted heterogeneity, whatever. That comes into play here. Tests of heterogeneity can be used to determine whether population effect sizes are either fixed or variable. A homogeneity test that yields non-significant results would support homogeneous population effect sizes and therefore a fixed effect model. All right, so we've decided on a model. Next, we need to choose a method. We have two methods to choose from: Hunter and Schmidt or Hedges and colleagues. Now, Field and Gillette report that Hunter-Schmidt method yielded the most accurate estimates of population correlation across a variety of situations. But note that Hunter and Schmidt is limited to random effects models. And as we'll see in a moment, Hedges and colleagues permits both fixed and random effects models. This is actually a bit more complicated. There's a 2005 paper by Field that has a table to help researchers decide between the two models, or methods rather. So if you're more interested in learning more about it, definitely check out that 2005 paper by Field. All right, so the Hunter and Schmidt process takes up an entire book, and obviously this is a very high-level overview. Ultimately, the calculations will be done behind the scenes with our software of our choice, so getting into the nitty-gritty of the formulas is a little bit beyond the scope of this presentation. But behind the scenes, the Hunter and Schmidt method is isolating and correcting the sources of error. Now, this method calculates the effect size by estimating a simple mean, weighted by the size of the sample upon which it was based. Once we have the effect size, we need to estimate how broadly this can apply by calculating a credibility interval. Now, you're likely more familiar with confidence intervals, which measures the precision of an estimate. A credibility interval measures whether validity can be generalized. So you can see quantifying the generalizability of our effect size is better served by a credibility interval rather than a confidence interval. Now, finally, a chi-square statistic is calculated to measure the homogeneity of the effect sizes. Now, as I said earlier, the Hedges and colleagues method allows for both fixed and random effects models. So if you're going the fixed model route, you'll definitely need to use the Hedges and colleagues method. Now, the calculation behind the scenes here get pretty complicated pretty quick. So again, if you want to learn more about the Hedges and colleagues method, read through that section in the Field and Gillette paper. But for our demonstration, we'll stick with the Hunter and Schmidt method and a random effects model. Now, because the statistical formula are so scary, we're just going to conduct the actual meta-analysis calculation using the software. Now, here you can choose between a wide variety of platforms. Our demonstration will include R and SPSS, but there's also purpose-built calculators online and software packages that you can download. You can also use Excel spreadsheets if you're a little more adventurous or have a good source with pre-built templates. And as we near the end of this 6-step method, we start to consider the inclusion of advanced analyses that can enhance or improve our meta-analysis. For this step, we will focus on how to estimate publication bias, or the file drawer analysis. We touched on this very briefly at the beginning of this lecture, where I mentioned that there's a potential for bias in using only unpublished studies to conduct, or rather using only published studies to conduct our meta-analysis. Now, this is not a trivial bias. Field and Gillette report that articles with significant findings are estimated to be 8 times more likely to be submitted for publication than studies with non-significant findings. And when it comes to publications, significant findings are 7 times more likely to be published. So in other words, journals are biased in reporting significant findings. So if your pool of research studies is limited only to published articles, you may be biasing your results towards significant findings. And so that brings us to Rosenthal's fail-safe N. Field and Gillette cite this as the earliest and most commonly used estimation of publication bias. Essentially, it was a method to estimate the number of unpublished articles. And so to compute Rosenthal's fail-safe N, we first convert each effect size to a z-score, then plug that into an equation based on the total number of studies in the meta-analysis and a constant of 2.706. The result would quantify the number of unpublished studies needed to make the population effect size non-significant. But there's a problem. There's been criticism of Rosenthal's fail-safe N due to its dependence on significance testing. A number of alternatives have been tried out over the years, but ultimately, these formulas are addressing the wrong question. It would be more interesting to know the basis or the bias in the data, what it is and how to correct it, instead of estimating some unknown value. So enter funnel plots. This plot displays effect sizes plotted against the sample size or standard error. You can see this on the example from Field and Gillette here on the screen, that effect size has been plotted on the x-axis and the standard error on the y-axis. Now, for a sample to be unbiased, it should show data points roughly symmetrical and in the shape of an inverted funnel. A lack of symmetry would reveal a sample with a publication bias. While you can generate such plots in SPSS, Field and Gillette recommend using R instead. They also caution against relying too heavily on the funnel plots and instead recommend that they are used as an initial indicator, or kind of a check for you towards the beginning of your research. Now, a fairly recent method developed by, I'm not sure how to say it correctly, but we'll go with Viva and Woods in 2005, actually corrects the population effect size based on the publication bias. And Field and Gillette recommend doing this calculation in R, and I will show that process once we get to the demonstration. So we've reached the final step in Field and Gillette's 6-step method of meta-analysis, and that is where we write up our findings. One of the articles cited in the Canvas folder is Rosenthal in 1995. Now, this is a great article that outlines reporting meta-analytic reviews. So if you're looking for very specifics on how to write up your meta-analysis, Rosenthal in 95 is a great source. Field and Gillette use this article as a springboard for their recommendations. The first and perhaps most important is to clearly articulate your search and inclusion criteria. Dr. Nyman is constantly telling us that researchers make a lot of decisions in the course of conducting our studies. We can make any decision we like as long as we can support it with literature and transparently justify our choice and reasoning. One of the key pieces of information you should report is which effect size measure you used, a fixed or random. And more than just saying which effect size measure you used, explaining why you chose that effect size is the important part. There are multiple techniques for meta-analysis, and a good researcher should clearly explain which was chosen and why. Rosenthal, Field, and Gillette recommend providing stem and leaf plots as a concise way to summarize the effect sizes used in our analysis. And finally, we need to include our publication bias analyses. Preferably those would include a variety of analyses, such as the funnel plot and the Viva and Woods sensitivity analysis. And that brings us to the live demonstration of meta-analysis. The sample files are available for download. That would be the scripts and the outputs from the folder on Canvas. We'll use that simple data set for a demonstration of a meta-analysis in both R and SPSS. As I begin this demonstration, I'd like to first share this quote from Andy Field, along with the most flattering screenshot of Dr. Field that I could find. So with that out of the way, let's take a look at Field's Discovering Statistics website, and there we will download the necessary files for our demonstration. You can see there are a number of files as well as very basic instructions on running the demonstration. Now I've downloaded all the files into a single folder on my desktop, which I have creatively named Demo. As far as what the files are, we can see there's a couple different varieties. First, we have the syntax files. These are the various different analyses that you can run with the data. We also have different data sets from which SPSS will run the analyses, and then sample outputs for us to verify that everything worked correctly. Now, I would recommend keeping the naming conventions the same. That's because the syntax references these files exactly. So if we change the names, it could cause some problems later. So I would recommend just keeping the exact naming conventions as they are. The only change you will need to make is to reference your own directory for each of the syntax files, and I'll show you how to do that once we get to that point. So now we are ready to head over to SPSS and begin our meta-analysis. We start by loading in our data set, and you can either select File and then Open, or just click the Open icon, the data set that you downloaded from the website. So go ahead and select Yes for the message about data encoding, and that's it. We have now loaded in all the data needed for our SPSS to run our meta-analysis. Now we need to input the syntax that will command the actual meta-analysis itself. Now earlier I quoted Andy Field saying meta-analysis in SPSS is not easily done. What he means is that you can't use the graphic user interface, so the GUI, only a special syntax, the one that he shares with you on the website. So in that sense, it's very similar to running a syntax in R. Loading the syntax is just like loading the data set. We click the open folder icon, select syntax, then locate the syntax file that you wish to open. And the syntax is pretty well set. You only need to change one line. That's to edit the working directory line to reflect the place where you store your files. To run the syntax code, go to the Run menu and select Run All. Once the analysis is complete, SPSS will open your output window. Now, I've copied this data over to a Word document for easier scrolling and viewing, so let's take a look at our results. The bulk of your meta-analysis results are right here on the first page, so let's walk through what some of these numbers mean. First is the number of studies, and this is the number of studies that you're analyzing, not necessarily the number of participants. So depending on how you're organizing or conducting your analyses, this may exactly equal the number of articles, or there may be multiple studies per article. The next section is your fixed effects model, and recall that we can choose between a fixed effects or random effects model. Now this SPSS syntax runs both, so it is pretty convenient to compare the results and see what you have. Within the field, or rather within the fixed effects model section, I'll point out a few numbers. First is the mean R. This is the mean effect size measured as Pearson's R, so just abbreviated as R. And of course, that was opposed to Cohen's D, or odds ratio, and so on. So for this study, the mean effect size is 0.580, with the lower and upper bounds of 0.52 and 0.633 respectively. The mean R is really the heart of your meta-analysis. This single number is showing the effect size across the studies that you're analyzing. Now, as we've learned, Pearson's R effect size is most commonly used in our field of social science research, and can range from -1 to +1, with 0 being no association at all, and then positive or -1 indicating perfect association, either positive or negative. So looking at our R value here of 0.58, we see that it is positive. This tells us that our meta-analysis has found a positive association between our study variables across the 10 studies that we're analyzing. However, with the value of 0.58, it is certainly not a perfect association. But before we settle in and start writing up our findings, we have two other models to consider: Hedges-Viva and Hunter-Schmidt. You'll see that these models each have different mean R values. Now, as a researcher, you need to select which model is most appropriate for your data and your specific meta-analysis. Now, all that to say, you really should have selected your model by the time you've settled on the goal of your research before you've even conducted your meta-analysis. In other words, choose a model first and then obtain the results of that model. Don't pick your model based on the results. Now, since we have both fixed and random effect data, let's compare them. Let's look at the homogeneity test, or goodness of fit. Now, compare the fixed effects of chi-squared with that of the Hedges-Viva model. Note that the results of the fixed effects model is significant. That means the sample size effects are not roughly equal, indicating the population effect sizes are likely not equal either. Therefore, a random effects model would better fit the data. And so let's now consider the mean effect R of the Hedges-Viva model. It indicates a mean of 0.612. What exactly does that mean? See what I did there? Effect sizes relates to the variance, or rather control of the variance. Now, according to Cohen, an R value of 0.50 indicates a large effect, where the correlation accounts for 25% variance. Now, Field and Gillette have a caution here. While cone is widely used as reference and even justification for qualifying the effect size as either large or small, Cohen's recommendation should not be blindly used and must be considered within the context of your own study and the peer literature. We see here the Rosenthal failsafe N, and earlier we talked about what this number represents. That is an estimation of the number of unpublished studies that would need to exist to turn a significant population effect size into a non-significant one. But again, as we discussed, any failsafe method is really addressing the wrong questions. It would be better to know the bias in the data one has and to correct for it. And this is where we look at funnel plots as developed by Light and Pillemer. This plot illustrates effect sizes plotted against a measure of the precision of the estimate. And in this case, it is the standard error. And as Field and Gillette explain, an unbiased sample should show data points that are symmetric around the effect size, and generally in the shape of a funnel, where the shape is reflecting the variability in effect sizes. So the less symmetry, the more likely we have a sample with publication bias. And that's because studies based on small samples show small effects, or rather showing small effects, are less likely to be published than studies with the same size but greater effects. Now, finally, Field and Gillette advised against using either Rosenthal's failsafe N or funnel plots as your full justification for mediating the publication bias. Instead, they recommend running more advanced analyses in R. So let's continue our meta-analysis demo and move over to R now. And once you open R, you'll need to find and open your syntax or source file. So within the syntax file, you'll only need to change your directory. I'm also going to point out that the syntax files are slightly different for Windows and Mac versions. So obviously this is the Mac version. And if you're running this on Windows, it will look very slightly different. Two different source files to download from the website. We'll go ahead and run the script. R is going to go through some drama as it runs all the calculations and such. At the end, you'll get a nice, neat little presentation of your sensitivity of effect size estimates to publication bias. So at this point, let's quickly recap where we are, how we got here. We conducted our meta-analysis in SPSS. That output gave us the Rosenthal failsafe N, but we learned that that isn't really accurately testing and correcting for bias. So we took a look at some funnel plots to further assess our bias. But still we aren't correcting for any potential bias, we're just getting some more insight into it. So to actually calculate and assess our bias, we've moved into R and run the syntax. Now this syntax was provided by Field and Gillette as part of their website and the demonstration, but was adapted from work by Viva and Woods. The syntax uses a data file that's generated by SPSS during our initial meta-analysis. Now let's take a look at the numbers that R has come up with. Now remember that we've decided on a random effects model, so we're only going to consider numbers associated with that model. First, we have the unadjusted parameter estimates. Now this corresponds roughly with the value that we saw in SPSS. We also see that this estimate, when converted back into Pearson's R, is also very close to what we see from SPSS, that value of 0.61. The difference is these numbers provide the values of the population effect size estimate corrected for 4 different selection bias models that were outlined by Viva and Woods. Now, in other words, we have now begun to correct for our publication bias. At this point, what you're really looking at or for is how different the R values are once corrected for that bias compared to the original effect size we got in SPSS. And remember that SPSS said that our unadjusted population effect size as R, Pearson's R, was 0.61. So we want to take a look at the 4 different scenarios from the Viva and Woods models. Now here, Field and Gillette say this about the comparison in this demo. Even applying a severe selection bias model, the population effect size drops only to 0.60. And as such, we can be confident that the strong effect identified in the meta-analysis is not compromised, even when applying corrections for a severe selection bias. So with that, we conclude our demonstration of doing a meta-analysis with SPSS and R. I do hope this video has been helpful in giving you a little taste of meta-analysis as a research tool. I definitely recommend reading a little bit more on the topic, and especially the Field and Gillette article. It's a very handy resource should you want to dig deeper on this topic. Again, that concludes the presentation. I thank you for your kind attention.
So that was a really
Well, hello there.
intense, review of meta-analysis, and that's only the introduction of it. How they come to the conclusion and how they statistically analyze their data. And I just wanted to point that out because you have to realize this. I hope gave you an insight as to why meta-analysis and systematic reviews fall at the top of your pyramid of hierarchy of evidence, because the depth of what they have to go into in terms of the research and statistically analyzing the data really proves like how solid the findings are and what it takes to get them. So I hope this was helpful. And next week we do have a quiz. We will be breaking into groups now in order to begin your meta-analysis grid. All right, thanks guys.